The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Hey, everybody, let's get going. Who here has heard of the FFT? That's most of you. So I first met Steve Johnson when he worked with one of my graduate students, now former graduate student, Matteo Frigo, and they came up with a really spectacular piece of performance engineering for the FFT, a system they call FFTW, for the fastest Fourier transform in the West. And it has, for over years and years, been a staple of anybody doing signal processing will know FFTW. So anyway, it's a great pleasure to welcome Steve Johnson, who is going to talk about some of the work that he's been doing on dynamic languages, such as Julia and Python.
Yeah, thanks.
Is that pretty accurate?
Yeah. So,
okay.
So I'm going to talk, as I said, about high-level dynamic languages and how you get performance in these. And so most of you have probably used Python or R or MATLAB. And so these are really popular for people doing technical computing, statistics, and anything where you want kind of interactive exploration. You'd like to have a dynamically typed language where you can just type x equals 3, and then 3 lines later decide, oh, x is an array, because you're doing things interactively. You don't want to have to be stuck with a particular set of types. And so there's a lot of choices for these. But they usually hit a wall when it comes to writing performance-critical code in these languages. And so traditionally, people doing some serious computing in these languages have a two-language solution. So they do high-level exploration and productivity and so forth in Python or whatever. But when they need to write performance-critical code, then you drop down to a lower-level language, Fortran or C or Python or one of these things, and you use Python as the glue for these low-level kernels. And the problem, and this is workable. I've done this myself. Many of you have probably done this. But when you drop down from Python to C or even to Python, there's a huge discontinuous jump in the complexity of the coding. And there's usually a loss of generality. Like when you write code in C or something like that, it's specific to a very small set of types. Whereas the nice thing about high-level languages is you can write generic code that works for a lot of different types. So at this point, there's often someone who pops up and says, oh, well, I do performance programming in Python. And everyone knows you just need to vectorize your code, right? So and basically what they mean is you rely on mature external libraries that you pass them a big block of data. It does a huge amount of computation and comes back. And so you never write your own loops. And this is great. This is good advice. If there's someone who's already written the code that you need, you should try and leverage that as much as possible, but somebody has to write those, and eventually that person will be you, and because eventually if you do scientific computing, you run into a problem inevitably that you just can't express in terms of existing libraries very, very easily or at all. So this was the state of affairs for a long time. And a few years ago, starting in Alan Edelman's group at MIT, there was a proposal for a new language called Julia, which tries to be as high level and interactive as it's a dynamically typed language, as MATLAB or Python and so forth. But general purpose language like Python, very productive for technical work, so really oriented towards scientific numerical computing. But you can write a loop and you write low-level code in that's as fast as C. That was the goal. The first release was in 2013, so it's a pretty young language. The 1.0 release was in August of this year. So before that point, every year there was a new release, 0.1, 0.2, 0.3, and every year it would break all your old code, and you have to update everything to keep it working. So now they said, okay, it's stable. We'll add new features. We'll make it faster. But from this point onwards, for at least until 2.0, many years in the future, it'll be backwards compatible. So there's lots of, so in my experience, this pretty much holds up. I haven't found any problem where I could, where there was a nice highly optimized C or Fortran code where I couldn't write equivalent code or equivalent performance, equivalently performing code in Julia, given enough time, right? Obviously, if something is, there's a library with 100,000 lines of code, it takes quite a long time to rewrite that in any other language. So there's lots of benchmarks that illustrate this. The goal of Julia is usually to stay within a factor of 2 of C. In my experience, it's usually within a factor of few percent that you can get if you know what you're doing. So there's a very simple example that I like to use, which is generating a van der Waals matrix. So you're given a vector of values, alpha 1, alpha 2 to alpha m, and you want to make an m by n matrix whose columns are just those entries to the 0th power, 1st power, squared, cubed, and so forth, element-wise. Right, so this kind of matrix shows up in a lot of problems. So most matrix and vector libraries have a built-in function to do this. So in Python, in NumPy, there's a function called numpy.vander to do this. And if you look at it's generating a big matrix, it can be performance critical, so they can't implement it in Python. So if you look at the NumPy implementation, it's a little Python shim that calls immediately to C. And then if you look at the C code, I won't scroll through it, but it's several hundred lines of code. It's quite long and complicated. And all that several hundred lines of code is doing is just figuring out what types and to work with, what kernels to dispatch to. And at the end of that, it dispatches to a kernel that does the actual work. And that kernel is also C code, but that C code was generated by a special purpose code generation. So it's quite, involved to get good performance for this while still being somewhat type generic, so that their goal is to have something that works for basically any NumPy array and any NumPy type, which is there's a handful, maybe a dozen scalar types that it should work with, right? So if you're implementing this in C, it's really trivial to write 20 lines of code that implements this, but only for double precision array, a pointer to a double precision array, right? So the difficulty is getting type generic in C. So in Julia, here's the implementation in Julia. It looks, at first glance, much like roughly what a C or Fortran implementation would look like. It's just implemented in the most simple way. It's just 2 nested loops. So just for basically, you loop across, and as you go across, you accumulate powers by multiplying repeatedly by x. Right? That's all it is, and it just fills in the array. The performance of the graph here is the time for the NumPy implementation divided by the time for the Julia implementation as a function of n for an n by n matrix. The first data point, I think there's something funny going on that's not 10,000 times slower, but for a 10 by 10, 20 by 20 array, the NumPy version is actually 10 times slower because it's basically the overhead that's imposed by going through all those layers. Once you get to 100 by 100 matrix, the overhead doesn't matter. And then it's all this optimized C code, code generation, and so forth is pretty much the same speed as the Julia code. Except the Julia code there, as I said, it looks much like C code would, except there's no types. It's vander x, there's no type declaration, x can be anything. And so in fact, this works with any container type as long as it has an indexing operation. And any numeric type, could be real numbers, could be complex numbers, could be quaternions, anything that supports a times operation. And there's also a call to 1. So 1 returns the multiplicative identity for whatever. So whatever group you're in, you need to have a 1. Right? That's the first column. But it might be a different type of 1 for a different object. Right? It might be an array of matrices, for example, and then 1 is the identity matrix. So, in fact, there are even cases where you can get significantly faster than optimize C and Fortran code. So I found this when I was implementing special functions, so things like the error function or polygamma function or the inverse of the error function. I've consistently found that I can get often 2 to 3 times faster than optimized C and Fortran libraries out there. partly because I'm just smarter than the people who wrote those libraries, but no, mainly because in Julia, I'm using basically the same expansions, the same series, rational functions that everyone else is using. The difference is that in Julia, it has built-in techniques for what's called metaprogramming or code generation. So usually the special functions involve lots of polynomial evaluations. That's what they boil down to. And you can basically write code generation that generates very optimized inline evaluation of the specific polynomials for these functions that would be really awkward to write in Fortran. You'd either have to write it all by hand or write like a separate routine, separate program that wrote Fortran code for you. So you can do this. So high-level languages allow you to do tricks for performance that it would be really hard to do in low-level languages. So mainly what I wanted to talk about is give some idea of why Julia can be fast. And to understand this, you also need to understand why is Python slow. And in general, what's going on in determining the performance in a language like this? What do you need in the language to enable you to compile it to fast code while still being completely generic, like this Vander function, which works on any type, any even user-defined numeric type, user-defined container type will be just as fast as there's no privileged. In fact, if you look at Julia, almost all of Julia is implemented in Julia, like integer operations and things like the really basic types. Most of that is implemented in Julia, right? I mean, obviously, if you're multiplying two 32-bit integers, at some point it's calling an assembly language instruction, but even that calling out to this assembly is actually in Julia. So at this point, I want to switch over to sort of a live calculation. So this is from a notebook that I developed as part of a short course with Alan Edelman, who's sitting over there, 18096 on performance optimization, high-level languages. And so I'm going to go through just a very simple calculation. Of course, you would never, I mean, in any language, usually you would have often have a built-in function for this, but it's just a sum function. It's just written up there. So we just have a list, an array of n numbers. We're just going to add them up, right? And if we can't make this fast, right, then we have real problems. We're not going to be able to do anything in this lesson. So this is the simple sort of thing where if someone doesn't provide this for you, you're going to have to write a loop to do this. So, and I want to look at it not just in Julia, but also in Python, in C, and set some in Python with NumPy, and so forth. So this document that I'm showing you here is a Jupyter notebook. Some of you may have seen this kind of thing. So Jupyter is this really nice. They provide this really nice browser-based front end where I can put in equations and text and code and results and graphs all in like one sort of Mathematica notebook-like document, and it can plug in different languages. So initially it was for Python, but we plugged in Julia, and now there's R, and there's 100 different languages that you can plug into the same front end. Okay, so I'll start with the C implementation of this. So this is a Julia notebook, but I can easily compile and call out to C. So I just made a string that has just, there's a 10-line C implementation. It's just the most obvious function that just takes in a pointer to an array of doubles and its length, and it just loops over them and sums them up. Right, just what you would do, and then I'll compile it with GCC-03 and link it to a shared library and load that shared library in Julia and just call it. So there's a function called ccall in Julia where I can just call out to a C library with zero overhead basically. So which is nice because you have lots of existing C libraries out there. You don't want to lose them. So I just say ccall. I'm going to call this csum function in my library. It returns a float64. It takes two parameters, a size t to float64. And I'm going to pass the length of my array and the array, and it'll automatically, a Julia array, of course, is just a bunch of numbers, and it'll pass a pointer to that under the hood. So do that, and I wrote a little function to call rel error that computes the relative error between the fractional difference between x and y. And I'll just check it. I'll just generate 10 to the 7th random numbers in 0, 1, and compare that to the Julia, because Julia has a built-in function called sum. That sums an array, and it's giving the same answer to 13 decimal places. So not quite machine precision, but there's 10 to the 7th numbers, so the error is kind of accumulated when you add it across. Okay, so, so I'm calling it, it's giving the right answer. And now I want to just benchmark this C implementation, use that as kind of a baseline for this. This should be pretty fast for an array of floating point values. So there's a Julia package called benchmark tools. As you probably know from this class, benchmarking is a little bit tricky. So this will take something, run it lots of times, collect some statistics, return the minimum time, or you can also get the variance and other things. So I'm going to get the number. B time is something called a macro in Julia. So it takes an expression, rewrites it into something that basically has a loop and times it and does all that stuff. Okay, so it takes 11 milliseconds to sum 10 to the 7th numbers, just with a straight C loop compiled with GCC-03, no special tricks. Okay, and so that's so that's 1 gigaflop basically, 1 billion operations per second. So it's not hitting the peak rate of the CPU, but of course there's additional calculations. This array doesn't fit in cache, and so forth. Okay. So now before I do anything in Julia, let's do some Python. But I'll do a trick. I can call Python from Julia, so that way I can just do everything from one notebook using a package I wrote called pycall. And pycall just calls directly out to libpython, so with virtually no overheads. It's just like calling Python from within Python. I'm calling directly out to libpython functions to call. I can pass any type I want and call any function and do conversions back and forth. Okay, so I'm going to take that array. I'll convert it to a Python list object. So I don't want to time the overhead of converting my array to a Python array, so I'll just convert it ahead of time. And just start with Python has a built-in function called sum, so I'll use the built-in sum function, and I'll get this Py object for it. I'll call it PySum on this list, and make sure it's giving the right answer. Okay, it is. The difference is 10 to the minus 13th again. And now let's benchmark it. Oops, there we go. So it takes a few seconds because it has to run it a few times and collect some statistics. Okay, so it took 40 milliseconds. That's not bad. It's 4 to 5 times slower than C, but it's pretty good, right? So why is it 5 times slower than C? Is it because the glib answer is, oh well, Python is slow because it's interpreted, but the sum function is actually written in C. Here's the C implementation of the sum function that I'm calling. I'm just linking to the GitHub code. There's a whole bunch of boilerplate that just checks with the type of the object, and then has some loops and so forth. And so if you look carefully, it turns out it's actually doing really well. And the reason it does really well is it has a fast path. If you have a list where everything is a number type, so then it has an optimized implementation for that case. But it's still 5 times slower than C. And they've spent a lot of work on it. It used to be 10 times slower than C, so a couple of years ago. So they do a lot of work on optimizing this. And so why aren't they able to get C speed? Since they have a C implementation of a sum, are they just dumb? No. It's because the semantics of the data type prevent them from getting anything faster than that. So, and this is one of the things you learn when you do performance in high-level languages. You have to think about data types, and you have to think about what the semantics are, and that greatly constrains what any conceivable compiler can do. And if the language doesn't provide you with the ability to express the semantics you want, then you're dead. And that's one of the basic things that Julia does. So what is a Python list? Right? So you can have 3, 4, right? Right? A Python list is a bunch of objects, Python objects, but the Python objects can be anything. They can be any type. So it's completely heterogeneous types. So of course, a particular list, like in this case, can be homogeneous, but the data structure has to be heterogeneous. Because in fact, I can take that homogeneous thing, at any point I could assign the third element to a string. right? And it has to support that. So think about what that means for how it has to be implemented in memory. So what this has to be, so this is a list of, in this case, 3 items. But what are those items? So if they can be an item of any type, right? They could be things, it could be another array, right? It could be of different sizes and so forth. You don't want to have an array where everything is a different size, first of all. So it has to be just an array of pointers, right? Where the first pointer is 3, it's to an object 3, the next one is 4, the next one is 2. Right? But it can't just be that. It can't just be pointer to, like, if this is a 64-bit number, it can't just be pointer to to one 64-bit value in memory, because it has to somewhere store what type this object is. So there has to be a type tag that says this is an integer. And this one has to have a type tag that says it's a string. Right? So this is sometimes called a box. So you have a value, you have a type tag, plus a value. Right? And so imagine what even the most optimized C implementation has to do, given this kind of data structure. OK, here's the first element. It has to chase the pointer, and then ask, what type of object is it? OK? Then depending on what type of object it is, OK, so I initialize my sum to that. Then I read the next object. I have to chase the second pointer, read the type tag, figure out the type. This is all done at runtime, right? And then, oh, this is another integer. That tells me I want to use the plus function for 2 integers. Okay, and then I read the next value, which may be, it's a floating. So the which plus function it's using depends upon the type of the object. It's an object-oriented language. I can define my own type, which has its own plus function, and it should work with sum. So it's looking up the types of the objects at runtime. It's looking at the plus function at runtime, and not only that, but each time it does a loop iteration, it has to add 2 things and allocate a result. That result in general might be has to be a box, because the type might change as you're summing through. Or if you start with integers and then you get a floating point value and then you get an array, right? The type will change. So each time you do a loop iteration, it allocates another box. So what happens is the C implementation has a fast path. If they're all like integer types, I think it doesn't reallocate that box for the sum it's accumulating all the time, and it caches the value of the plus function it's using. So it's a little bit faster, but still it has to inspect every type tag and chase all these pointers for every element of the array. Whereas the C implementation of sum, if you imagine what this compiles down to, right? For each loop iteration, what does it do? It increments a pointer to the next element, it knows that at compile time the types are all float64, so it fetches a float64 value into a register, and then it has a running sum in another register, calls one machine instruction to add that running sum, and then it checks to see if we're done, has an if statement there, and then goes on. Right? So just a few instructions in a very tight loop here, whereas each loop iteration here has to be lots and lots of instructions to chase all these pointers to get the type tag. And that's in the fast case where they're all the same type and it's optimized for that. So, where was I? Wrong thing. So that's the Python sum function. Now, many of you who've used Python know that there's another type of array, and there's a whole library called NumPy for working with numerics. What problem is that addressing? So the basic problem is this data structure. This data structure is, as soon as you have a list of items that can be any type, you're dead. Right? There's no way to make this as fast as a C loop over a double pointer. So to make it fast, what you need to have is a way to say, oh, every element of this array is the same type, so I don't need to store type tags for every element. I just store a type tag once for the whole array. So there's a tag there's a type, which is, say, float64. Okay. There's maybe a length of the array. And then there's just a bunch of values, one after the other. So this is just 1.0, 3.7, 8.9, and each of these are just 8 bytes, an 8-byte double in C notation, right? So it's just one after the other. So it reads this once, reads the length, and then it dispatches to code that says, okay, now basically dispatches to the equivalent of my C code. All right, so now once it knows the type and the length, then, okay, it says it runs this. Okay? And that can be quite fast. And the only problem is you cannot implement this in Python. So Python doesn't provide you a way to have that semantics, to have a list of objects where you say they all have to be the same type. There's no way to enforce that or to inform the language of that in Python. And then to tell it, oh, for this type, since these are all the same type, you can throw away the boxes. Like every Python object looks like this. So there's no way to tell Python, oh, well, these are all the same types. So you don't need to store the type tags. You don't need to have pointers. You don't need to have reference counting. You can just slam the values into memory one after the other. It doesn't provide you with that facility, and so there's no way to, you can make a fast Python compiler that will do this. So NumPy is implemented in C. Even with, some of you are familiar with PyPy, which is an attempt to make a fast, like a tracing JIT for Python. So when they ported to NumPy to PyPy, or they attempted to, even then, they could implement more of it in Python, but they had to implement the core in C. Okay, but given that, I can do this. I can import the NumPy module into Julia, get its sum function, and benchmark the NumPy sum function. And okay, again, it takes a few seconds to run. Okay, and it takes 3.8 milliseconds. So the C was 10 milliseconds. So it's actually doing faster than the C code, almost a little over twice as fast, actually. And what's going on is their C code is better than my C code. Their C code is using SIMD instructions. So you probably, and at this point, I'm sure that you guys all know about these things where you can read in 2 numbers or 4 numbers into like one giant register, and one instruction add all 4 numbers at once. Okay, so what about if we go in the other direction? We write our own Python sum function. So we don't use the Python sum implemented in C. I write our own in Python. So here's a little mysum function in Python. Only works for floating point. I initialize s to 0.0, so it really only accumulates floating point values, but that's okay. And then I just loop for x and a, s equals s plus x, return s. Right, this is the most obvious thing you would write in Python. Okay, check that it works. Yeah, error is 10 to the minus 13th. It's giving the right answer. And now let's time it. So remember, C was 10 milliseconds. NumPy was like 5 milliseconds. And then the built-in Python was like, the sum was 50 milliseconds operating on this list. Now, so now we have C code operating on this list with 50 milliseconds. And now we have Python code operating on this list. And that is 230 milliseconds. Right, so it's quite a bit slower. And it's because basically in Python, in the pure Python code, there's no way to implement this fast path that checks, oh, they're all the same type, so I can cache the plus function and so forth. I don't think it's feasible to implement that. And so basically then on every loop iteration, it has to look up the plus function dynamically and allocate a new box for the result and do that 10 to the 7th times. So now, so there's a built-in sum function in Julia. So this just to benchmark that it's actually implemented in Julia. It's not implemented in C. I won't show you the code for the built-in one because it's a little messy because it's actually computing the sum more accurately than the loop that I've done. It uses. So that's 3.9 milliseconds. So it's comparable to the NumPy code. Okay, so it's also using SIMD, but so this is also fast. And so now, So why can Julia do that? So it has to be that the array type, first of all, has the type attached to it. So you can see the type of the array is an array of flow 64. So there's a type tag attached to the array itself. So somehow that's involved. So it looks more like a NumPy array in memory than in this, than a Python list. You can make the equivalent of a Python list that's called an array of any. So if I convert this to an array of any, so an array of any is something where the elements types can be any Julia type, and so then it has to be stored as something like this, as an array of pointers to boxes. And when I do that, let's see. There it is. Then it's 355 milliseconds. So it's actually even worse than Python. So the Julia, Python, they spent a lot of time optimizing their code paths for things that had to allocate lots of boxes all the time. So in Julia, it's usually understood that if you're writing optimized code, you're going to do it not on arrays of pointers to boxes, like if you're going to write it on homogeneous arrays or things where the types are known at compile time. Okay, so let's write our own Julia sum function. This is the Julia sum function. There's no type declaration. It works on any container type. I initialize S for this function called 0 for the element type of A. So it initializes it to the additive identity. So it'll work on any container of anything that supports a plus function that has an additive identity. So it's completely generic. It looks a lot like the Python code, except for there's no 0 function in Python. And let's make sure it gives the right answer. It does. And let's benchmark it. All right. So this is the code you'd like to be able to write. You'd like to be able to write high-level code that's a straight loop. Unlike the C code, it's completely generic, right? It works on any container, anything you can loop over, and anything that has a plus function, right? So an array of quaternions or whatever. And a benchmark, it's 11 milliseconds. It's the same as the C code I wrote in the beginning. It's not using SIMD. So instruction side, that's where the additional factors of 2 come, but it's the same as the non-SIMD C code. And in fact, if I want to use SIMD, there's a little tag you can put on the loop to tell, so it's compiling this with LLVM. You can say, tell LLVM to try and vectorize the loop. Sometimes it can, sometimes it can't. But something like this, it should be able to vectorize it. It's simple enough. You don't need to hand code SIMD instructions for a loop this simple. Yeah?
Why don't you always put the S in default?
So yeah, why isn't it the default? Because most of the code, like most code, the compiler cannot auto-vectorize. So it increases the compilation time, and it often bloats the code size for no benefit. So it's really only relatively simple loops on doing simple operations on arrays that benefit from SIMD. So you don't want it to be there. Yeah, so now it's 4.3 milliseconds. So it's about the same as the NumPy and so forth. It's a little slower than the NumPy. It's interesting. A year ago when I tried this, it was almost exactly the same speed as the NumPy. And then since then, both the NumPy and the Julia have gotten better, but the NumPy got better more. So there's something going on with basically how well the compiler can use AVX instructions by, it seems like. We're still investigating what that is. But it's an LLVM limitation, looks like. So, and as I said, it's still completely type generic. So if I make a random array of complex numbers, and then I sum them, call it which one am I calling now? Am I calling the vector? My sum is the vectorized one, right? So complex numbers, each complex number is 2 floating point numbers. So it should take about twice the time to naively think, right? So twice the number of operations to add the same number of complex numbers, the same number of real numbers. Yeah, and it does. It takes about 11 milliseconds. So for 10 to the 7th, which is about twice the 5 milliseconds it took for the same number of real numbers. And the code works for everything. So why? Okay, so what's going on here? So we saw this mySum function. I'll just take out the SIMD for now. And we did all that. Okay. Okay, so and it works for any type. It doesn't even have to be an array. So for example, there's another container type called a set in Julia, which is just an unordered collection of unique elements. But you can also loop over it. If it's a set of integers, you can also sum it. And I'm waiting for the benchmarks to complete. So let me allocate a set. And so there's no type declarations here. Like my sum A, there was no A has to be an array of particular type, or even it doesn't even have to be an array, right? So a set is a different data structure, and so it's a set of integers. It's the sets are unique. So if I add something to already the set, it's in there. It won't add it twice, and it supports like fast checking if is 2 in the set, is 3 in the set. It doesn't have to look through all the elements. It's a hash internally. But I can call my MySum function on it, and it sums up 2 plus 17 plus 6 plus 24, which is hopefully 49. Right? So, okay, so what's going on here? So suppose you define the key. One of the keys there's several things that are going on to make Julia fast. So one key thing is that when you have a function like this MySum, or even here's a simpler function, f of x equals x plus 1. When I call it with a particular type of argument, like an integer or an array of integers or whatever, then it compiles a specialized version of that for that type. So here's f of x equals x plus 1. It works on any type supporting plus. So if I call f of 3, so here I'm passing a 64-bit integer. When it did that, it says, okay, x is a 64-bit integer. I'm going to compile a specialized version of f with that knowledge. And then when I call it with a different type, 3.1, now x is a floating point number. It'll compile a specialized version with that value. If I call it with another integer, it says, oh, that version was already compiled. That's why we use it. So it only compiles it the first time you call it with a particular type. If I call it with a string, it'll give an error because it doesn't know how to add plus to a string. So in particular, okay, so what is going on? So we can actually look at the compiled code. So something called code, there's functions called code, these macros called code LLVM and code native that say, okay, when I call f of 1, what's the do people know what LLVM is? You guys, okay. So LLVM, right, compiles to bytecode first, and then it goes to machine code. So you can see the LLVM bit code or bytecode or whatever it's called, and you can see the native machine code. So here's the LLVM bytecode that it compiles to f of 1. So it calls add I64 0. It calls basically one LLVM instruction, which turns into one machine instruction. Load effective address is actually a 64-bit addition function instruction. So let's think about what had to happen there. So if you have f of x equals x plus 1, now you want to compile for x is a int 64. So a 64-bit integer, or in Julia we'd say x : int 64. So : means this is of this type. Okay, so this is a 64-bit integer type. So what does it have to do? It first has to figure out what plus function to call. So plus, it has lots of different, there's a plus for 2 matrices, a plus for lots of different things. And so depending on the types of the arguments, it decides on which plus function to call. So it first realizes, oh, this is an integer. Oh, this is an integer. This is also a 64-bit integer. So that means, so I'm going to call the plus function for 2 integers. So I'm going to look into that function. And then, oh, that one returns an int 64. So that's the return value for my function. And oh, by the way, this function is so simple that I'm going to inline it. So it's type specializing. And this process of going from x as an integer to that, to figuring out the type of the output, is called type inference. Okay? So in general, for type inference, is given the types of the inputs, it tries to infer the types of the outputs, and in fact, all intermediate values as well. Now, what makes it a dynamic language is that this can fail. So in some languages like ML or some other languages, you don't really declare types. But they're designed so that you give the types of the inputs, you can figure out everything. And if it can't figure out everything, it gives an error, basically. It has to infer everything. So Julia is a dynamic language. This can fail, and it have a fallback of, if it doesn't know the type, it can stick things in a box. Right? But obviously the fast path is when it succeeds. And one of the key things is you have to try and to make this kind of thing work in a language. You have to design the language so that at least for all the built-in constructs, the standard library, or in general in the culture for people designing packages and so forth, to design things so that this type inference can succeed. And I'll give a counterexample to that in a minute. Right? So, and this works recursively. So now suppose I define a function g of x equals f of x times 2. Okay? And then I call g of 1. So it's going to say, OK, x here is an integer. Okay? I'm going to call f with an integer argument. Oh, I should compile f for an integer argument, figure out its return type, use its return type to figure out what times function to call, and do all this at compile time, right? Not at runtime, ideally. So we can look at the LLVM code for this, and in fact, so this is, remember, f of x adds 1 to x, and then we're multiplying by 2. So the result computes 2x plus 2. And LLVM is smart enough, so f is so simple that it inlines it, and then LLVM is smart enough that I don't have to, well, I know, it does it by one shift instruction to multiply x by 2, and then it adds 2. So it actually combines the times 2 and the plus 1. So it does constant folding. Okay? And you can continue on. If you look at h of x equals g of x times 2, then that compiles to one shift instruction to multiply x by 4, and then adding 4. Right? So you want this. So this process cascades. So, and you can even do it for recursive functions. So here's a stupid implementation of a Fibonacci number calculation of recursive implementation, right? So this is given n, it's an integer. Okay, if n is less than 3, it returns 1. Otherwise, it adds the previous 2 numbers. I can call this in the first 10 integers. Here's the first 10 Fibonacci numbers. There's also a cute notation in Julia. You can say fib dot. So if you do f dot arguments, it calls the function element-wise on a collection and returns a collection. So f dot 1 to 10 returns the first 10 Fibonacci numbers. And I can call, there's a function called code warn type that'll tell me it'll tell me the output of type inference. So n is a 1, and it goes through, this is kind of a hard to read format, but this is like after one of the compiler passes called lowering. But yeah, it's figure out the types of every intermediate call. So here it's invoking main.fib, it's recursively, and it's figured out that the return type is also an N64, so it knows everything. Okay, so you'll notice that here I declared a type. I said that this is an integer. Okay, I don't have to do that for type inference. This doesn't help the compiler at all, because it does type inference depending on what I pass. So what this is more like a filter. It says that if I pass, this function only accepts integers. If you pass something else, it should throw an error. Because I don't want this function, because if I pass 3.7, right, if I fill out any number, if you look at the 3.7, I can check whether it's less than 3. It can call it recursively. I mean, the function would run. It would just give nonsense, right? So I want to prevent someone from passing nonsense for this. So that's one reason to do a type declaration. But another reason is to do something called dispatch. So what we can do is we can define different versions of a function for different arguments. So for example, another nicer version of that is a factorial function. So here is a stupid recursive implementation of a factorial function, right, that takes an integer argument and just recursively calls itself on n minus 1. So I can call it on 10 factorial. Okay. If I want 100 factorial, I need to use a different type, not 64-bit integers. I need some arbitrary precision integer. And And since I said it was an integer, if I call it 3.7, it'll give an error. Okay, that's good. But now I can define a different version of this. So actually, there is a generalization of factorial to arbitrary real, in fact, even complex numbers, called the gamma function. And so I can define a fallback that works for any type of number that calls a gamma function from someplace else, and then if I can pass it a floating point value, I can. If you take the factorial of minus a half, it turns out that's actually square root of pi. So if I square it, it gives pi, right? So now I have one function, and I have two methods, right? So these types here. So there's a hierarchy of types. So this is what's called an abstract type, which most of you probably have seen. So there's a type called number, and underneath there's a class of subtypes called integer, and underneath there's, for example, int 64 or int 8 for 8-bit or 64-bit integers, and underneath number there's actually another subtype called real, and underneath that there's couple subtypes, and then there's say float 64 or float 32 for a single precision 32-bit floating point number, and so forth. So there's a hierarchy of these things. When I specify something can take integer, I'm just saying so this type is not help the compiler. It's to provide a filter. It says this method only works for these types, and this other method only works. My second method works for any number type. So I have one method that works for any number type. Oops, here it is. One method that works for any number type, and one method that only works for integers. So when I call it for 3, which ones does it call? Because I actually call both methods. And what it does is it calls the most specific one. It calls the one that's sort of farthest down the tree. So if I have a method that's defined for number and one defined for integer, if I pass an integer, it'll do this. If I have one that's defined for number, one that's defined for integer, and one that's defined specifically for int 8, and I pass an 8-bit integer, it'll call that version. Right? So it gives you a filter. But in general, you can do this on multiple arguments. So this is like the key abstraction in Julia, something called multiple dispatch. So this was not invented by Julia. I guess it was present in Smalltalk, in Dylan. It's been in a bunch of languages. It's been floating around for a while, but it's not been in a lot of mainstream languages, not in a high-performance way. And you can think of it as a generalization of object-oriented programming. So I'm sure all of you have done object-oriented programming in Python or C++ or something like this. So in object-oriented programming, typically the way you think of it is you say you have an object. It's usually spelled like object.method, x, y, for example, right? And what it does is this type, the object type, determines the method, right? So you could have a method called plus, but I would actually call a different plus function for a complex number or a real number or something like that, or a method called length, right, which for a Python list would call a different function than for a NumPy array, right? In Julia, the way you would spell the same thing, you'd say method so you wouldn't say object.method, right? So you don't think of here you think of the object as sort of owning the method, right? And Julia, the object would just be maybe the first argument. In fact, under the hood, if you look in Python, for example, the object is passed as an implicit first argument called self, right? So it actually is doing this. It's just different spelling of the same thing. But as soon as you write it this way, you realize what Python and what OOP languages are doing is they're looking at the type of the first argument to determine the method. But why just the first argument? So in a multiple dispatch language, you look at all the types. So this is sometimes, in Julia, this would sometimes be called single dispatch. because this determining the method is called dispatch. Right, figuring out which function is the spelled length, which function actually are you calling that's dispatching to the right function. So this is called multiple dispatch. And it's clearest if you look at something like a plus function. All right, so a plus function, all right, if you do a plus b, right, which plus you do really should depend on both a and b. Right? It shouldn't depend on just a or just b. And so it's actually quite awkward in languages, in OOP languages like Python or especially C++, to overload a plus operation that operates on sort of mixed types. As a consequence, for example, in C++, there's a built-in complex number type. Right? So you can have a complex float or complex double, complex int, complex with different real types. But you can't add a complex float to a complex double. You can't add a single precision complex number to a double precision complex number, or any mixed operation, because any mixed complex operation, because it can't figure out who owns the method. It doesn't have a way of doing that kind of promotion, right? So in Julia, so now you can have a method for adding a float 32 to a float 32, but also a method for adding I don't know. Let's see. Here's adding a complex number to a real number, for example. Right? You want to specialize, or a real number to a complex number. You want to specialize things. In fact, we can click on the link here and see the code. So a complex number to a real number in Julia looks like this. It's the most obvious thing. It's implemented in Julia. Plus complex to real creates a new complex number, but you only have to add the real part. You can leave the imaginary part alone. And this works on any complex type. Okay. So there's too many methods for. Okay, I can shrink that. Let's see. So I can talk about, there's another type inference thing called, I'll just mention it briefly. So one of the things you have to do to make this type inference process work is, given the types of the arguments, you have to figure out the type of the return value. Okay, so that means when you define a function, it has to be what's called type stable. That the type of the result should depend on the types of the arguments and not on the values of the arguments. Because the types are known at compile time, the values are only known at runtime. And it turns out if you don't have this in mind, I mean, in C you have no choice but to obey this. But in something like Python, a dynamic language like Python or MATLAB, if you're not thinking about this, it's really easy to design things so that doesn't work, so that's not true. So a classic example is the square root function. All right, so suppose I pass an integer to it. Okay, so the square root of this is square root of 5, right? The result has to be a floating point number, right? So it's 2.23, whatever. So if I do square root of 4, of course that square root is an integer. But if I return an integer for that type, then it wouldn't be type stable anymore. Then the return value type would depend on the value of the input, whether it was a perfect square or not. Right? So it returns a floating point value, even if the input is an integer. Yes?
If you have enough methods defined for like a bunch of different types, is the lookup for the right function, like, can that become really slow?
Well, since the lookup comes at compile time, so it's really kind of irrelevant. At least if type inference succeeds. If type inference fails, then it's runtime. It's slower, but it's not like it's like a tree search, so it's not as slow as you might think. But most of the time you don't worry about that, because if you care about performance, you want to arrange your code so that type inference succeeds. So you prototype, maybe this is something that you do in performance optimization. Like when you're prototyping, you don't care about types. You say x equals 3, and the next line you say x equals an array, whatever. But when you're optimizing your code, then you tweak it a little bit to make sure that things don't change types willy-nilly, and that the types of a function depend on the types of the arguments, not on the values. So the reason I mentioned square root is what really confuses people at first is if you take square root of -1, you might think you should get a complex value. Right? And instead, it gives you an error. Right? And because that's basically what are the choices here? It could give you an error. It could give you a complex value. But if it gave you a complex value, then the return type of square root would depend upon the value of the input, not just the type. So MATLAB, for example, if you take square root of -1, it'll happily give you a complex number. But as a result, if you have MATLAB has a compiler, right? And has many, many challenges. But like one simple thing to understand is if the MATLAB compiler sees a square root function anywhere in your function, even if it knows the inputs that are real, it doesn't know if the outputs are complex or real unless it can prove that the inputs were positive or non-negative, right? And that means it could then compile 2 code paths for the output, right? But then suppose it calls square root again, or some other function, right? You quickly get a combinatorial explosion of possible code paths because of possible types. And so at some point you just give up and just put things in a box. But as soon as you put things in a box and you're looking up types at runtime, you're dead, right, from a performance perspective. So Python actually so if you want a complex result from square root, you have to give it a complex input. So in Julia, complex number, I is actually im. They decided I is too useful for loop variables. So I and j. So im is the complex unit. And if you take square root of a complex input, it gives you a complex output. So Python actually does the same thing. So in Python, if you take square root of a negative value, it gives an error, unless you give it a complex input. But Python made other mistakes. So for example, in Python, an integer is guaranteed never to overflow. If you add 1 plus 1 plus 1 over and over again in Python, eventually it'll overflow the size of a 64-bit integer, and Python will just switch under the hood to an arbitrary precision integer, right? Which seemed like a nice idea probably at the time. And the rest of Python is so slow that like the performance cost of this test, it makes no difference in a typical Python code, but it makes it very difficult to compile. Because that means if you have integer inputs and you see x plus 1 in Python, the compiler can't just compile that to one instruction, because unless it can somehow prove that x is sufficiently small. So in Julia, integer arithmetic will overflow, but the default integer arithmetic is 64 bits. So in practice, that never overflows unless you're doing number theory. And you usually know if you're doing number theory, and then you use arbitrary precision integers. It was much worse in the days, like this is something people worried a lot, before you were born, when there were 16-bit machines, right? And integers, it's really, really easy to overflow 16 bits, right? Because the biggest sign value is then 32,767, right? So it's really easy to overflow. So you're constantly worrying about overflow. And even 32 bits, the biggest sign value is 2 billion. It's really easy to overflow that, even just counting bytes, right? You can have files that are bigger than 2 gigabytes easily nowadays. So people worried about this all the time. But with 64-bit integers, basically a 64-bit integer will never overflow if it's counting objects that exist in the real universe, like bytes or loop iterations or something like that. So then you just say, okay, it's either 64 bits or you're doing number theory, you should use big ints. So let me talk, the final thing I want to talk about, let's see, how many are you in time? Good. Is defining our own types. So this is where, this is the real test of the language, right? So it's easy to make a language where there's a certain built-in set of functions and built-in types, and those things are fast. So for example, for Python, there actually is a compiler called Numba that does exactly what Julia does. It looks at the arguments, type specializes things, and then calls LLVM and compiles it to fast code. But it only works if your only container type is a NumPy array, and your only scalar type is one of the 12 scalar types that NumPy supports. If you have your own user-defined number type or your own user-defined container type, then it doesn't work. And user-defined container types is probably easy to understand why that's useful. User-defined number types are extremely useful as well. So for example, there's a package in Julia that provides a number type called dual numbers. And those have the property that if you pass them into the function, they compute the function and its derivative. And it's just a slightly different, it basically carries around function and derivative values and has a slightly different plus and times and so forth that just do the product rule and so forth, and it just propagates derivatives. And then if you have Julia code like that Vandermonde function, it'll just compute its derivative as well. Okay, so I want to be able to define my own type. So a very simple type that I might want to add would be points, 2D vectors in two space, right? So, of course, I could have an array of 2 values, but an array is a really heavyweight object for just 2 values, right? If I know at compile time there's 2 values, that I don't need to have a pointer to block. I can actually store them in registers. I can unroll the loop over these. Everything should be faster. You can get an order of magnitude in speed by specializing on the number of elements for small arrays compared to just a general array data structure. So let's make a point. Okay, so this is. And I'm going to go through several iterations. One of it, starting with the slow iteration. I'm going to define a mutable struct. Okay, so this will be a mutable object where I can add a call point that has 2 values, x and y. It can be of any type. I'll define a plus function that can add them. And it does the most obvious thing. It adds the x components, adds the y components. I'll define a 0 function, that's the additive identity, that just returns the 0.00, and then I can construct an object 0.34. I can say 0.34 plus 0.56. It works. It can hold, actually, right now it's very generic and probably too generic. The real part can be a floating point number, and the imaginary, the x can be a floating point number here, and the y is a complex number of 2 integers. Or even I could make a string and an array that doesn't even make sense. So I probably should have restricted the types of x and y a little bit just to prevent the user from putting in something that makes no sense at all. Okay, so these things, they can be anything. So this type is not ideal in several ways. So let's think about how this has to be stored in memory. So this is a 0.1. Say 0.1, 1, 3.7, right? So in memory, there's an x and there's a y, but x and y can be of any type, so that means they have to be pointers to boxes. There's a pointer to int 1, and there's a pointer to a float 64 in this case. 3.7. So, this already we know this is not going to be good news for performance, right? And it's mutable. So that mutable struct means if I take p equals a point, I can then say p dot x equals 7. I can change the value, okay, which seems like a harmless thing to do, but actually is a big problem, because, for example, if I make an array of 3 p's. Okay, and then I say p dot y equals 8, and I look at that array, it has to change the y component, right? So if I have a p, or in general, if I have a p that's looking at that object, if this is an object you can mutate, it means that if I have another element, a q, that's also pointing to the same object, and I say p dot x equals 4, then q.x had better also be 4 at that point. So to have mutable semantics, to have the semantics of something you can change, and other references can see that change, that means that this object has to be stored in memory on the heap as a pointer to 2 objects, so that you can have other pointers to the same object, and I mutate it, and the other references see it. It can't just be stuck in a register or something like that. It has to be something that other references can see. So this is bad. So I can call 0.1.aa calls the constructor element-wise, and this a is this array of 10 to the 7th random numbers I was benchmarking on before that was taking 10 milliseconds. Okay, and if I can sum it. I can call the built-in sum function on this. I can even call my sum function on this because it supports a 0 function, and so it supports a plus. So here I have an array. If I scroll back up, I have an array here of 10 to the 7th values of type 0.1. So that the type of 0.1 is attached to the array. So the array in memory, so if I have an array of 0.1, the 1 here means it's a one-dimensional array. There's also 2D, 3D, and so forth. That looks like a 0.1 value, a 0.1 value, a 0.1 value. But each one of those now, has to be a pointer to an X, and a Y, which themselves are pointers to boxes. Right, so assuming this is going to be really slow because there's a lot of pointer chasing, it has to, at runtime, check what's the type of X, what's the type of Y. And in fact, it took, instead of 10 milliseconds, it took 500 or 600 milliseconds. So to do better, we need to do two things. So first of all, X and Y, we have to be able to say what type they are. Okay? It can't be just any arbitrary old thing that has to be a pointer to a box. Okay? And the point object has to be immutable. It has to be something where if I have P equals something, Q equals something, I can't change P and expect Q to see it. Otherwise, if it's mutable, they have to be stored as those semantics have to be implemented as some pointer to an object someplace, and then you're dead. So I can just say struct. So struct now is not mutable. It doesn't have the mutable keyword. And I can give the arguments types. I can say they're both float 64. And then X and Y are both the same type. They're both 64. But floating point numbers, I'll define plus the same way, 0 the same way. And now I can add them and so forth. But now if I make an array of these things, and if I say p.x equals 6, it will give an error. It says, oh, you can't actually mutate. Don't even try to mutate it because we can't support those semantics on this type. But that means, so that type is actually, if you look at that in memory, what the compiler is allowed to do, and what it does do for this is if you have an array of 0.2, 1, then it looks like just the X value, the Y value, the X value, the Y value, and so forth, where each of these are exactly one 8-byte float 64. And all the types are known at compile time. And so if I sum them, it should take about probably 20 milliseconds, right? Because summing real numbers was 10 milliseconds. And this is twice as many because it has to sum the X's, sum the Y's. And let's benchmark it. And let's see. Oh, actually, summing the real numbers took 5 milliseconds. So something should take about 10. Let's see. Is that still true? Yeah, it took about 10. So actually, the compiler is smart enough. It stores this. So first of all, it stores this in line as one big block, consecutive block of memory. And then when you sum them, remember our sum function. This is the built-in sum, but our sum function will work the same way. The compiler, LLVM, will be smart enough to say, oh, I can load this into a register, load Y into a register, have a tight loop where I basically call one instruction to sum the X's, one instruction to sum the Y's, and then repeat. Right, so it's about as good as you could get. But you paid a big price. We've lost all generality, right? These can only be two 64-bit floating point numbers. I can't have two single precision numbers or two. So this is like a struct of two doubles in C, right? So if I have to do this to get performance in Julia, then that would suck. Basically, I'm basically writing C code in a slightly higher level syntax. I'm losing that benefit of using a high level language. So the way you get around this is you define. What you want is to define something like this 0.2 type, but you don't want to define just one type. You want to define a whole family of types. You want to define this for two float 64s, two float 32s. In fact, you want to define an infinite family of types for two things of any type you want, as long as they're two real numbers, two real types. And so the way you do that in Julia is a parameterized type. This is called parametric polymorphism. It's similar to what you see in C++ templates. So now I have a struct. It's not mutable. 0.3, but the curly braces, T, it says it's parameterized by type T. So X and Y, I've restricted it slightly here. I've said X and Y have to be the same type. I didn't have to do that, but I could have had two parameters, one for the type of X, one for the type of Y. But most of the time you'd be doing something like this. You'd want them both to be the same type. But they could be both float 64s, both float 32s, both integers, whatever. So T is any type that less than colon means is a subtype of. So T is any subtype of real. Could be float 64, could be int64, could be int8, could be big float, could be a user-defined type. It doesn't care. So this is really not, it's a point 3 here is a whole hierarchy. Is not so I'm not defining one type. I'm defining a whole set of types. So point 3 is a set of types. There's a point 3 in 64. There's a point 3 float 32, for float 64, and so on. Infinitely many types, as many as you want, and basically it'll create more types on the fly just by instantiating. So for example, otherwise it looks the same. The plus function is basically the same. I add the x components, the y components. The 0 function is the same. Except now I make sure there's zeros of type t, whatever that type is. And now if I say 0.34, now I'm instantiating a particular instance of this. And now that particular instance of 0.3 will have one, this is an abstract type, will have one of these concrete types. And the concrete type it has in this case is a 0.3 of 2 in 64s, two 64-bit integers. Okay, and I can add them. And actually adding mixed types will already work because the plus, the addition function here, it works for any 2 0.3s. I didn't say they had to be 0.3s of the same type. So any 2 of these, they don't have to be 2 of these. They could be one of these and one of these. And then it determines the type of the result by the type of the return. It does type inference. So if you have an 0.3 of 2 in64s and 0.3 of 2 float 32s, it says, oh, p.x is an in64, q.x is a float 64. Oh, which plus function did I call? Oh, there's a plus function for that mixed thing, and it promotes the result of float 64. So that means that sum is float 64, the other sum is float 64. Oh, then I'm creating a 0.3 of float 64s. So this kind of mixed promotion is done automatically. You can actually define your own promotion rules in Julia as well. And I can make an array. And so now, if I have an array of 0.3 float 64, so this type is attached to the whole array. And this is not an arbitrary 0.3, it's a 0.3 of 2 float 64s, so it gets stored again as just 10 to the 7th elements of x, y, where each one is 8 bytes, 8 bytes, 8 bytes, one after the other. The compiler knows all the types, so when you sum it, it knows everything at compile time, and it will sum 2 of these things by loaded this into a register, load this into a register, call one instruction, add them. And so the sum function should be fast. So we can call the built-in sum function, we can call our own sum function. Our own sum function, I didn't put SIMD here, so that's going to be twice as slow. But yeah. Yeah?
Would this work with SIMD?
Yeah. Yeah, in fact, if you look, the built-in sum function is implemented in Julia. It just has an @SIMD on the sum. So yes, so LLVM is smart enough that if you give it a struct of 2 values and it load them, and if you tell it that adding these 2 values to these 2 values, these 2 values to these 2 values, it will actually use SIMD instructions. I think. Oh, maybe not. No, wait. Did my sum use SIMD? Confused. I thought it did. I thought I removed it. Yeah. So maybe it's not smart enough to use SIMD. I've seen in some cases where it's smart enough to use, yeah. Okay, so they're the same speed. Okay, no, I take it back. So maybe LLVM is not smart enough in this case to use SIMD automatically. We could try putting the SIMD annotation there and try it again. But I thought it was, but maybe not. Let's see, let's put SIMD. So redefine that, and then just rerun this. So it'll notice that I changed the definition. It'll recompile it. But the beat time, since it times it multiple times, the first time it calls it's slow because it's compiling it, but it takes the minimum over several times. Let's see. Yeah, I mean, this is a problem in general with vectorizing compilers, is they're not that smart if you're using anything other than just like an array of an elementary data type. Yeah, no, it didn't make any difference, so I took it back. So for more complicated data structures, you often have to use SIMD instructions explicitly, and there is a way to do that in Julia, and there's a higher level library on top of that. You can basically create a tuple and then add things, and it'll do SIMD acceleration. But yeah. So anyway, so that's the upshot here. I mean, there's a whole bunch of, like the story of like why Julia can be compiled to fast code. It's like a combination of lots of little things, but there are a few big things. One is that it's specialized thing as compile times, but of course you can do that in any language. So that relies on designing the language so that you can do type inference. It relies on having these kind of parameterized types, and giving you a way to talk about types and attach types to other types. So the array, you notice probably, let's see. Now that you understand what these little braces mean, you can see that the array is defined in Julia as another parameterized type. It's parameterized by the type of the element and also by the dimensionality. So it uses the same mechanism to attach types to an array, and you can have your own user. The array type in Julia is implemented mostly in Julia, and there are other packages that implement their own types of arrays that have the same performance. One of the goals of Julia is to build in as little as possible, so that there's not like some set of privileged types that the compiler knows about, and everything else is second class. It's like, user code is just as good as the built-in code. And in fact, the built-in code is mostly just implemented in Julia. There's a small core that's implemented in C for bootstrapping, basically. So having parameterized types, having another technicality is having all concrete types are final in Julia. So that means you can't, so a concrete type is something you can actually store in memory. So like 0.3864 is something you can actually have, right? An object of 2 integers is that type, so it's concrete, right? As opposed to this thing, this is an abstract type. You can't actually have one of these. You can only have one of the instances of the concrete types. So, but this is final. It's not possible to have a subtype of this. Because if you could, then you'd be dead, because this is an array of these things. If the compiler has to know it's actually these things and not some subtype of this, right? So, whereas in other languages, like Python, you can have subtypes of concrete types. And so then even if you said this is an array of a particular Python type, you wouldn't really know it's that type, or it might be some subtype of that. That's one of the reasons why you can't implement NumPy in Python. There's no way to say, no, this is really that type and nothing else in the language level. Yeah?
How does compilation in Julia work?
Oh, yeah. So it's calling LVM. So basically the stage is you call. So there's a few passes. Okay. So and one of the fun things is you can actually inspect all of the passes and almost intercept all of them practically. So of course, typing code like this, first it gets parsed. Okay, and you can a macro, those things that I'm calling with @ actually are functions that are called right after parsing. They can just take the parsed code and rewrite it arbitrarily. So you can extend the language that way. So it's first, but then it's parsed, maybe rewritten by a macro, and then you get an abstract syntax tree. And then when you call it, let's say f of 3. Then it says, oh, x is an integer in 64. Then it runs the type inference pass. It tries to figure out what's the type of everything, which version of plus to call, and so forth. Then it decides whether to inline some things. And then once it's done all that, it spits out LLVM bytecode and calls LLVM and compiles it to machine code, and then it caches that someplace. So for the next time you call f, f of 4, f with another integer. It's calling this. It doesn't repeat the same process. It's noticed. Oh, it's cached. So that's yeah. But it's at the lowest level, it's just LLVM. So there's tons of things I haven't showed. So I haven't showed you. I mentioned metaprogramming. So it has this macro facility. So you can basically write syntax that rewrites other syntax, which is really cool for code generation. You can also intercept it after the type inference phase. You can write something called the generated function that basically takes, because at parse time it knows how things are spelled. and you can rewrite how they're spelled, but it doesn't know what anything actually means. It just knows X is a symbol. It doesn't know X is an integer or whatever. It just knows the spelling. So when you actually compile f of X, at that point it knows X is an integer. And so you can write something called a generated or a staged function that basically runs at that time and says, oh, you told me X is an integer? Now I'll rewrite the code based on that. And so this is really useful there's some cool facilities for multidimensional arrays, because the dimensionality of the array is actually part of the type. So you can say, oh, this is a 3-dimensional array, I'll write 3 loops. Oh, you have a 4-dimensional array, I'll write 4 loops. And it can rewrite the code depending on the dimensionality with code generation. So you can have code that basically generates any number of nested loops depending on the types of the arguments, and all the generation is done at compile time after type inference, so it knows the dimensionality of the array. Yeah, so there's lots of fun things like that. Of course, it has parallel facilities. And they're not quite as advanced as Silk at this point, but that's sort of the direction they're heading. There's no global interpreter lock like in Python. There's no interpreter. So there's a threading facility, and there's a pool of workers, and you can spawn and you can thread a loop, and the garbage collection is threading aware, so that's safe. And they're gradually having more and more powerful runtimes, hopefully eventually hooking into some of Professor Lyserson's advanced threading compiler, taper compiler, or whatever it is. And there's also, from most of what I do in my research is more coarse-grained distributed memory parallelism. So running on supercomputers and stuff like that, and there's MPI, there's a remote procedure call library, there's different flavors of that. Yeah. So, any other questions? Yeah.
How do you implement the big number type?
The big num type in Julia is actually calling GIMP. That's one of those things. Let me just so let me create a new notebook. So if I say big int 3000, okay, and then I'd say that to the say factorial. I think there's a built-in factorial of that, right? So. So this is called a big num type, right? It's something where the number of digits changes at runtime. So of course, these are orders of magnitude slower than hardware things, because basically it has to be implemented as a loop of digits in some base. Right? When you add or multiply, you have to just loop over those at runtime. These big num libraries, they're quite large and heavily optimized, and so nobody's re-implemented one in Julia. They're just calling out to a C library called the GNU multi-precision library. And for floating point values, there's something called big float. It's a big float of pi. Is that I can actually just let's set precision. Big float to 1,000. That's 1,000 binary digits, and then say big float of pi, and so now it's more. By the way, yeah, you might have. So I can have a variable alpha hat sub 2 equals 17. That's allowed. That's always fun. All that's happening here is that Julia allows almost arbitrary Unicode things for identifiers. So I can have let me make it bigger. So you can have an identifier koala. Right. So. So there's two issues here. So one is just you have to have a language that allows those things as identifiers. So Python 3 also allows Unicode identifiers, although I think Julia, out of all the existing, the common languages, probably has the widest Unicode support. Most languages only have a allow a very narrow range of Unicode characters for identifiers. So Python would allow the koala, but Python 3 would not allow with alpha hat sub 2. Because it doesn't, the numeric subscript Unicode characters it doesn't allow. The other thing is how do you type these things? And that's more of an editor thing. And so in Julia, we implemented initially in the REPL and in Jupyter, and now all the editors support. You can just do tab completion of LaTeX. I can type gamma tab, and it tab completes the Unicode character. I can say dot, and it puts a dot over it, and backslash superscript 4, and it puts a 4, and that's that's allowed. So it's quite nice. So like when I'm typing emails and I put equations in emails, I go to the Julia REPL and tab complete all my LaTeX characters so that I can put equations in emails, because it's the easiest way to type these Unicode math characters. But yeah, so that's on IPython borrowed this, so you can now do the same thing in the IPython notebooks as well. So yeah, it's really fun when you're writing. Finally, because if you read old math codes, especially old Fortran codes or things like, you see lots of variables that are named alpha hat or something like that, alpha hat underscore 3. It's so much nicer to have a variable that's actually alpha hat sub 3. So that's cute.
Steve, thanks very much.
Yep, thanks.
This was great. We are, as Steve mentioned, looking actually at a project to merge the Julia technology with the Silk technology. And so we're right now in the process of putting together a grant proposal. And if that gets funded, there may be some UROPs.